So, we have seen that if you look at the TTT diagram for plain carbon steel, the nose of the curve is very close to the origin, that means it is order of seconds, and we would like to add alloying elements for various reasons, and one of the reasons is to move the nose of the TTT diagram to the right, so that we can employ a less severe quench to obtain full martensite. This implies that we increase the hardenability of the material. We also noted, like for instance, suppose even though I may apply a very severe quench on the surface of the material, the interior of the material is dependent on the thermal conductivity of the material and therefore may feel a less severe quench. Therefore, it is all the more imperative to move the TTT diagram to the right. This also avoids residual thermal stresses which are generated during the severe quench. Typically, many alloying elements are added, each one of them giving certain benefits, and a combination of alloying elements are also added to give better properties to the material. Some of these common alloying elements are chromium, manganese, tungsten, molybdenum, etc. In this current set of lectures, we will not go into all the details of alloy steels, but we will keep our focus on this aspect, that how it affects the TTT diagram, and broadly of course outline what are the benefits of adding alloying elements. The C curves of pearlite and bainite transformations overlap in the case of plain carbon steels, as we have seen, and in alloy steels we will see that they can be represented by separate C curves. That means even a constant cooling rate experiment can give you bainite, unlike in the case of plain carbon steels where you need an isothermal hold to obtain bainite. So, what is the broad role of alloying elements? They are added, for instance, to plain carbon steel to increase the hardenability. So, they are added to provide fine distribution of alloy carbides during tempering. They are added to increase resistance to softening on tempering. They are added for corrosion and oxidation resistance. They also give us strength at elevated temperatures, and they can often increase the elastic limit. Now, there are many more benefits which are not listed here, especially when added in a combination. They can give a unique combination of properties which are not available in plain carbon steels. Now, of course, all these alloying elements also combat some of the negative points which are there in plain carbon steels, like low hardenability, loss of hardness on tempering. That means there is severe loss of hardness on tempering, low corrosion and oxidation resistance, and low strength at high temperatures. Now, this increased hardenability automatically implies that we can make it easier to obtain properties throughout the larger section more easily. Now, these alloying elements also alter the temperature at which the transformation occurs, alter the solubility of carbon in alpha or gamma ion, and alter the rate of various reactions. So, there are a lot of complex things which these alloying elements do, but in this set of lectures we will not be able to go into detail into all these aspects, but we will take up a few points, especially with regard to heat treatment and the aspect I mentioned, that the effect on the TTT diagram. We should of course note that when you add a second alloying element, we have already seen previously that it may actually segregate or phase separate, and this could be deleterious. For instance, suppose you add phosphorus, which is not an intentional adding element, for instance present as an impurity, may segregate to the grain boundaries and cause problems. Sulfur can do the same thing. This alloying element may go into the solid solution, as you have seen before, or actually may form a compound. And which of these ways do we want to influence the properties is done via this microstructure engineering which we are studying. So, in this lectures we will worry about hardenability, and we will see that how this alloy carbides also are produced as a fine distribution which gives us superior properties. The role of very many elements in more than one context can be very diverse, but a small listing is mentioned here. For instance, phosphorus dissolves in ferrite and larger quantities form iron phosphide, which causes cold shortness and makes your material brittle. So, that means we want to avoid phosphorus in the material. Sulfur can cause hot shortness, again that means during deformation at high temperatures, at forging temperatures we have poor ductility, and therefore sulfur also should be avoided in most materials. But there are good elements, for instance chromium for instance improves corrosion resistance, it is a ferrite stabilizer, it gives you a high hardness to strength ratio and hardness or strength, and typically more than 11% chromium forms a passive barrier, that means it gives you good corrosion resistance to iron. So, a person who is working on steels should also know the role of each one of these alloying elements, the synergistic effects of these alloying elements, and how they should be added so that they do not segregate, etc. But as I mentioned that we will not go into details at this point of time. One point which might be noteworthy at stage is that suppose I am plotting the hardness of material along with the percentage of alloying element. If you add chromium, you would note that the hardness increases with the percentage of chromium. Okay. But additionally, suppose you are able to add carbon. So, this first curve is for chromium. Suppose I add chromium and add percentages of chromium, I note that my hardness increases with percentage of chromium in the material. But additionally, suppose I am adding carbon. So, this gives a further benefit to the fact that chromium is already there. So, if you have a chromium carbon steel, then I have an increased hardness also. Similarly, the case of manganese, pure manganese gives you an increased hardness, but manganese along with carbon gives, that means for a fixed percentage of manganese, here say 2%, I can get a higher hardness if carbon is present in 0.1%. Though that implies that this in the solid solution form, the alloying elements increase hardness, but the major contribution to hardness comes from carbon. But the point is that these alloying elements increase the hardenability, which has to be an important point which is to be noted. When you add these alloying elements, for instance, if you add chromium, chromium is a BCC structure and is a ferrite stabilizer. That means that if I add chromium in increasing percentage, then for instance, this is 0% chromium, this is my boundary of the gamma phase field at high temperatures. So, this is the boundary. If I add more and more chromium, you can see that the gamma phase field actually shrinks, because gamma is FCC and chromium is a ferrite stabilizer. Therefore, this phase field decreases, and at a certain critical percentage of chromium, you can see that 15%, the phase field has been reduced to such a small region. That means that if I add a ferrite stabilizer, then the gamma phase field increases. On the other hand, suppose I add an austenite stabilizer like manganese or nickel, which are both FCC structures, then the austenite phase field actually expands. So, these are some of the things which you would like to note when you are actually adding an alloying element, that what is its crystal structure, what role does it play in stabilizing or increasing or decreasing the various phase fields as compared to the original iron carbon diagram. So, this is a point we wanted to stress, that now this is a TTT diagram for nickel chrome moly steels. The first point we would note, of course, is that now there are separate branches for the, and this is a schematic, we will come to a more actual looking curve in the next diagram, that you would note that the pearlitic transformation curve, C curve, is now distinct from the benitic transformation C curve. So, that is the most important first point you would note. Now, this is a nickel chrome moly low alloy steel, that means you have added nickel, chromium and molybdenum to plain carbon steel, and now this is an alloy steel. Now, the second point anybody would note from this diagram is that the nose for formation of martensite, that means the nose which has to be avoided, now has been pushed to the order of about a minute. That implies now, instead of quenching at a rate which was very severe, for instance, initially I had to quench from the gamma phase field at a very severe rate, and of course, I am drawing a straight line, log scale, they have to look like curved lines. Now, we can actually quench at a less severe rate to produce martensite. So, this implies I need to employ a less severe quench to produce martensite. So, now, what does this imply? That my residual thermal stresses are also less, and my overall quenching process becomes less vigorous. That means, suppose I quench a steel, I need to worry about if bubbles are forming, which can actually reduce your cooling rate. Now, I do not have to worry about that, and further I can now harden larger cross sections of the material throughout. That means, I will get a uniform hardness across larger cross sections, and we had noted before that suppose I am talking about plain carbon steel, then you would note that even though at my surface I may produce a martensite, we had considered the cylinder before, and on the surface you may get martensite and high hardness, the hardness may actually fall towards the center, because in the core you may have only pearlite. Therefore, such problems can be alleviated to a large extent by using an alloy steel, in which case my TT diagram has moved to the right hand side. So, this is my direction which the TT diagram has moved. Now, for instance, what is the reason that this TT diagram is moving to the right? Initially, of course, the carbon had to partition itself between alpha and Fe3C. Suppose you had an gamma which was giving my alpha and Fe3C in my pearlitic transformation. Now, if you have an alloying element, for instance, which is present in gamma, say for instance, now in this case it is nickel, this nickel has additionally to partition between the alpha and Fe3C, and nickel being a substitutional alloying element is sluggish in its diffusion, and therefore, it takes a longer time for the pearlitic transformation to start and to complete. So, this is my pearlite start curve, and this is my pearlite finish curve. So, this partitioning issue, that now my alloying element has to partition between two phases, the alpha and Fe3C. In addition, of course, to the carbon, which is, say, I am talking about 0.8% carbon gamma, then this carbon also has to partition, because alpha is very low of carbon, Fe3C is 6.67% carbon. So, in addition to the carbon being partitioned between alpha and Fe3C, now the alloying elements and each has its equilibrium solubility in alpha and Fe3C. This is true for nickel, this is also true for chromium in the current case, and also to molybdenum. That means all these alloying elements have to partition between the alpha phase and Fe3C phase, which implies that now my overall eutectoid transformation is sluggish and my TT diagram is to the right. So, we can see that there are many properties which can improve by forming an alloy steel like the nickel moly low alloy steel, but additionally you have these benefits in terms of the practical process of producing martensite, which is the quenching, and also the ability to obtain a complete martensite across the cross section. Now, this is a diagram for another alloy steel, which is now it contains 0.42% carbon, 0.78% manganese, 1.79% nickel, 0.8% chromium, and 0.33% molybdenum. That means that now this has all the alloying elements in small percentages. Nickel is an austenite stabilizer, manganese is an austenite stabilizer, while chromium is an BCC element which stabilizes the ferritic phase. Now, all these alloying elements have now to partition between the alpha and Fe3C phase, and that means that now my overall T diagram is going to be sluggish. And here, like before, we are having the extra arm which corresponds to the ferritic transformation, because now this is an hypoeutectoid steel, and we have the other phase transformations. But the important point to note is that we have a separate C curve for the bainite and a separate C curve for the pearlitic phase. There are other complications to this curve which we are not considering in detail, but this is similar to the schematic we considered before, that we have two separate C curves, and now if I can avoid the nose of this curve and quench at a certain high rate, then I can produce my martensite starting from this austenitic phase. So, I am sorry, this is a little intersection here. So, both I can avoid the nose here. So, this is my correct curve. So, I can produce martensite. Therefore, and suppose I intersect the nose of the curve, then there will be a partial formation of bainite, which is not possible of course in the case of the plain carbon steels. So, there are certain benefits of working with alloy steels, and one of them we have considered here in detail. The other benefits, of course, the person is interested may go through different texts, will give you a lot of these things in detail. Previously, we have already seen that how does the hardness vary here with the microstructure, and we pointed out that this is a very, very important chart when we want to understand the properties. That, for instance, suppose a student of material science, as I pointed out, it should be well versed with what we call microstructure engineering. In other words, not only does he engineer his properties by using suitable crystal structures, like he knows that FCC is more ductile than VCC, but also additionally he manages his microstructure so as to get an optimum set of properties. We had noted that means that suppose I ask a question that what is the hardness or the tensile strength of 0.8% carbon steel, I pointed out this would be an ill posed question, and one needs to understand what is the heat treatment given, what is the microstructure, so that the properties come out. So, for the same 0.8% carbon steel, we can have a wide range of hardnesses as we saw before, starting from 16 RC to 65 RC, and also along with the change in the hardness, we saw there is also a change in ductility and other properties. Now, similarly, we will note some other properties which are now important, and we will see what is the effect of carbon and also the effect of the quenching process. These are all done on samples, and none of these tests should be taken ideally. They are just schematics tests, so that we can understand the overall concepts involved, and more accurate tests have to be done to actually get the true nature of the stress strain diagram. So, in this case, of course, I am plotting engineering stress with engineering strain, and I am doing so for 3 materials. 2 of them are 0.8% carbon steels. One has been slowly cooled, and when you slowly cool, we produce pearlite. So, this, in other words, should have a pearlitic microstructure. And when we quench it, we know that we produce martensite, and there could be some retained austenite. Now, if you take a 0.4% carbon steel, we know that we have already seen that with the reduction in carbon percentage, the microstructure now consists of pro-eutectoid ferrite followed by pearlite, and also the TT diagram for a 0.4% carbon steel is different from that of the 0.8% carbon steel. Now, for the 0.4% carbon steel, you note that these curves perhaps are not ideal, and you would like to, the true curve may look something slightly different. So, you may have a curve like this and you see that 0.8% carbon steel has a certain ductility, but the point. So, this is my 0.4% carbon steel, sorry, this is the one I am going to mark in yellow. So, this is my 0.4% carbon steel for which my curve is like this. So, the 0.4% carbon steel has certain amount of ductility, but the strength is lower than the 0.8% carbon steel. That means, by adding more carbon, I am increasing the strength of the material. But what is happening to the ductility? You see that there is a fall in ductility along with the increase in strength. So, the 0.8% carbon steel has a lower ductility as compared to the, of course, in this case I am not using the true measure of ductility, here I am using percentage elongation, but the true measure is not the strain or the percentage elongation, but has to be the percentage reduction in area, because after necking starts most of the deformation is localized to close to the neck. That means, when I am doing a test on a cylindrical specimen like this, what is expected to happen is that it will form a neck, and during this necking process most of the deformation is localized here, and therefore, percentage reduction in area is a better measure of ductility as compared to the strain or the percentage elongation. But here we are looking at the overall characteristics, and we can take a few take home messages, but with increasing carbon, though I have an increased strength, but I have lower ductility. On the other hand, suppose I take the same 0.8% carbon steel and quench it to produce martensite. Now, you notice that this material is very brittle, and any pre-existing cracks or quench cracks actually lead to the failure of the material. That means, it is not able to reach its true yield strength because of the crack propagation. We know that a ductile material is one in which the yield strength is lower than the fracture strength. A brittle material is one in which the yield strength is more than the fracture stress. In other words, I approach in a brittle material, I approach fracture before I cause plastic yielding, and you know fracture is related to the presence of cracks and in a material, and these cracks of course could be pre-existing cracks, they could be quench cracks which have come from processing, they could be surface cracks introduced by machining, etc. Or and this yield strength is related typically to the formation to the motion of dislocations. They are of course edge and screw dislocations or a mixed dislocation. Therefore, we see that when you quench this 0.8% carbon steel to produce martensite, because of its extreme brittle nature, it actually fails at very low strains. That means, in the it does not give you any much of plastic deformation. So, here we can see that the properties of a material are drastically altered by heat treatment, or what we can call as microstructure engineering, and this theme of course we have used plain carbon steel to illustrate, but this does not mean that this is limited to this case. You can use microstructure engineering even to engineer properties like coercivity, magnetic coercivity, etc. Now, so looking at this plot now, we can the summary of the tensile test curves is that if you have same percentage carbon, but different microstructures, you can see that the ductility is severely limited. So, this is 0.8% carbon steel, but it is slowly cooled giving perlite, while the martensitic microstructure gives you a very low ductility and the material fails at very low strains. Now, on the other hand, 0.8% carbon steel, 0.4% carbon steel, which is lower carbon, gives you higher ductility, but it has got a lower strength, because this carbon itself can give you a solid solution strengthening. Now, the same thing is also reflected in the hardness data, and again I would warn you that these are schematics or tests done on some routine industrial samples, but more controlled tests can give you actually numerical data which might be more accurate. Now, if you look at the hardness data, you note that I am having 3 samples, 0.6% carbon steel, 0.8% carbon steel and 1% carbon steel, and all the while you can see that with increasing carbon percentage my hardness is actually increasing. Now, if you take now my 0.8% carbon steel, which means that I am now a eutectoid composition, and quench it, then you notice that you can obtain a martensitic microstructure which is very hard. So, I can increase my hardness by increasing the carbon percentage along this curve, or I can take a fixed percentage of carbon like my 0.8% carbon and do a quenching, and which can give me a very high hardness, and this is a viscous hardness which is being measured here. So, of course, we all know that for 0.6% carbon steel we have a microstructure which contains pro-eutectoid ferrite, and in this case we have a pro-eutectoid cementite. So, I can increase my hardness by this carbon increment, which is my solid solution strengthening, or I can quench to produce martensite, which is a very hard phase, and there can be a considerable increase in the hardness. That means that I can clearly see that by doing microstructure engineering, I can alter the properties severely, and this gives me a handle on the properties further to the handle I get from the compositions. Okay, that means that I can alter the composition to get a specific set of properties, but further I can use these compositions to engineer my microstructure to get various structure dependent properties, which are very different from that in the absence of the heat treatment. And as I pointed out, we can also do a thermomechanical treatment. The second example we will consider today is the example of precipitation hardening in an aluminum copper alloy. This here again we do a detailed steps of heat treatment, understanding the various parameters involved, the process involved, to engineer the microstructure so as to give an high strength in a material which is otherwise not so hard. So, in precipitation hardening, we have seen that the presence of dislocations weaken the crystal, and this weakening we saw is a few orders of magnitude. That means, we can cause easy plastic deformation because of the presence of dislocations. If we can put, there are two ways of course hardening the material, either hinder the motion of dislocations or remove dislocations altogether, but we had already pointed out that removing dislocations altogether is not a good strategy, because dislocations may nucleate in service, causing the weakening of the crystal. Therefore, putting hindrance to the dislocation motion is a good idea, and we have seen before that this can be done via various methods like solid solution, making the solid solution cold working, etc., or giving a fine grain sized material. One of the methods is to actually produce fine precipitates which can impede the motion of dislocations, and such an impediment as to be, to get a fine precipitate, we have to engineer my heat treatment so as to get that. Suppose I am talking about strength of aluminum, which is about 100 MPa, which means that aluminum is actually a very superb structural material. It has got a good surface finish, it is lightweight, it can easily be cut, etc., and it's because of the aesthetic appeal and its easy ability to form and cut, it would form a good structural material. But the big problem with aluminum is that it is being an FCC structure, it is actually very ductile. So, one of the methods to increase its strength of course is to cold work it, but the other is to form an alloy like duralumin, and with proper heat treatment, and for instance now duralumin consists of aluminum and copper and other alloying elements, we can increase the strength to about 5 times, which is 500 MPa, which is a very good news that now I am alloying, and following the alloying I am doing a heat treatment, and for doing this heat treatment I have a knowledge of the phase diagram and the TTT diagram so as to engineer my heat treatment to get the desired properties. Now, let us look at the aluminum copper phase diagram, and I am interested in the copper rich aluminum rich end, because this is where the sloping solvus line of the phase diagram lies. So, in this aluminum copper phase diagram, the copper aluminum rich end, you have the liquid phase and you have the alpha and theta phases which form on slow cooling. That means, now suppose I take an alloy which is say for instance anywhere here, then my final microstructure would consist of alpha and theta, theta being the equilibrium phase, about whose crystal structure we will be talking sometime soon. Now, we are interested not in this part of the phase diagram, but in the lower copper percentage, and we are talking about of this region where there is about 4% copper, and this is a model system aluminum 4% copper, not only to see the engineering applications of precipitation hardening, but also to understand the various fundamental processes which occur during such a heat treatment. Now, this line is a sloping solvus line, that means that the solubility falls with temperature. That means, suppose at high temperatures I have a certain solubility for of copper in alpha, that means now my copper is dissolved in the alpha matrix, but then when I am cooling I will cross the solvus line, and that means that part of the suppose this is my tie line here, I will construct a tie line here and find out say for this temperature what are my phase fractions of alpha, and this arm of the so this is my fulcrum F and say x y. So, the fulcrum y line is proportional to the amount of alpha in the material. That means that if I slowly cool I will produce a theta precipitate, and normally when slowly cooled the morphology is such that the theta precipitate is very large. That means that I would have theta in my matrix, and the overall size of these theta precipitates, because will be very large, because I would have a few nuclei which grow very large, and therefore, I would have a coarse precipitate morphology of theta phase in the matrix. Now, this such a material is not very good for hindrance of dislocation motion. That means that suppose I had a, let me go to the board and explain you, and we have seen this before, that suppose I have a very fine distribution of precipitates in the material vis-a-vis coarse precipitates in the material. So, because now these precipitates are very coarse, the distance between those precipitates are large, and now if a dislocation is being pinned, this distance is now say L, actually the inner distance is L. Now, the tau max, the shear stress benefit is GB by L. That means, larger the L, lower the strength. On the other hand, suppose I have a fine distribution of precipitates, and now we have pinning centers from here to here, and this is my distance L prime. That implies now tau max prime is equal to GB by L prime, and therefore, tau max is greater than tau. That means that this, say this is tau max. So, this shear strength I get by a fine stress precipitate distribution, because now what we are assuming that we are actually operating a double ended Frank-Reed source. In other words, this dislocation to move, we will have to actually bend here, assuming these are incoherent precipitates, and for that we need to apply the tau max. That means an higher shear strength as compared to just motion of dislocations in an unimpeded matrix. Therefore, if I have precipitates which are far apart and they are coarse, they give a lesser hardening as compared to a fine distribution of precipitates. Now, how do I obtain a fine distribution of precipitates is the reason we are considering this phase diagram. So, let me summarize that you have this transformation which is alpha FCC with 4% copper at 550 degrees Celsius here, when slowly cooled gives you alpha FCC with 0.5% copper at room temperature, and the equilibrium precipitate which is a composition of CuAl2 which is a tetragonal phase. That means that it has got lower symmetry than the alpha phase which is a cubic phase, and this contains about 52% of copper. So, most of the copper goes into the theta phase and less of copper is present in the alpha, which anyhow has a low solubility for copper at lower temperatures. Now, this, as I pointed out, slow cooling gives rise to a coarse theta precipitate which is not good for impeding dislocation motion, and the benefit I was talking about tau max is GB by L. Now, to avoid this formation of this coarse precipitate, and again we are not altering the composition, we are keeping the composition of aluminum 4% copper, we follow a series of heat treatments, and these heat treatments have been labeled A, B and C. So, what are we doing in these heat treatments? Of course, is first of course assuming that I have somebody gives me a slowly cooled aluminum alloy with 4% copper, that means I would already have a combination of alpha phase and the theta phase which is a lower symmetry tetragonal phase. And as you know that if the system has a lower symmetry and it is intermetallic, then typically the Pearl stress of such a intermetallic would be larger. So, we expect that theta phase, the dislocation motion will be more difficult within the theta phase. Now, the heat treatment cycles I would follow to get a fine distribution of precipitates is what has been labeled A, B and C. So, I start with my material as received, which is now contains alpha and theta phases, theta being the equilibrium precipitate, and I assume that it is in the coarse state. I heat it above the solvus line first using during the A step to produce a solid solution, uniform solid solution alpha. So, by heating it and holding it, all my theta precipitate will dissolve and I will get an uniform solid solution alpha. So, I will have to hold long enough for that. So, typically the temperatures I can heat to is about 550 degrees Celsius, which is above the solvus line of this phase diagram. So, we are heating somewhere here. So, heating in this temperature regime so as to get an uniform solid solution alpha. In the second stage, what I do is that I quench this material. In step B, I quench it to room temperature, and during this quench process, two things are important to note. One is that I get a super saturated solid solution. This is now similar to for instance, when I opened a Coca-Cola bottle, when I under pressurize the system, and therefore, the carbon dioxide has been super saturated in the aerated drink with respect to the high pressure. That means, now I have a similar to that, here we have a, it is like also like suppose I dissolve sugar in water at high temperature. That means, at room temperature I can only dissolve a certain amount of sugar in water or a certain amount of salt. By heating the solution, I can dissolve more of sugar, but then suppose I immediately allow I cool the system very fast, then I would note that all the sugar cannot immediately come out of the solution, which we have known is called the nucleation barrier, opposes this, and therefore, you will have a super saturated solid liquid solution of sugar in water. Similarly, here we have a super saturated solution of copper in alpha ion. Additionally, during the quenching process, we have an increased vacancy concentration, because as we know, the vacancy concentration depends arrheniously on the temperature. That means, at higher temperature we had a higher vacancy concentration, but when we quenched it, there is no time for all the vacancies to escape. So, therefore, we will end up with of course, some of the vacancies may be lost, but some vacancies are still trapped within the lattice, and therefore, you have an increased vacancy concentration in step B. In step C, what we do is that we reheat the material to certain low temperature, and we will see what is the why this temperature 200 degrees Celsius comes when we consider in the coming slides, but this temperature is definitely much lower than the original solutionizing treatment. So, we have the solutionizing treatment first, then we have the quenching treatment, and finally, we have a process known as aging. And the reason this word aging is used in this context is that originally one of the investigators who discovered this process left his aluminum at solid solution at room temperature, and then later on returned to find that the hardness of the material had increased. When he looked under the microscope, the optical microscope, he could not locate any microstructural features which had changed, but somehow the material had aged so as to give an increased hardness. We will see now, because of powerful electron microscopy and other techniques, that we now know the basis of why that hardening took place, and what is as we pointed out the micromechanisms involved. And so, the third step we follow to get this fine precipitate is aging treatment, in which case we heat to a low temperature. This temperature could be around 180 or 200 degrees Celsius, and this gives us a fine precipitates inside the alpha matrix. So, let me summarize this slide, these three steps. Number 1, aluminum is reasonably soft and has a low yield strength. I can increase the strength by various methods like cold working, solid solution strengthening, or grain size refinement, but an additional technique here is that by precipitation hardening, in which case I use a aluminum 4% copper alloy, which can give me an considerable, and plus other alloying elements, can give me a considerable benefit up to a factor of 5. Now, the heart of this whole thing is the aluminum copper system has a sloping solvus line, and I can decrease, the solubility decreases with decreasing temperature, but if I slowly cool it, I get my equilibrium theta precipitate, which is very coarse, which is not good for the hindrance of dislocations, and therefore, I would like to produce a fine distribution of precipitates in the aluminum matrix. What is the nature of these precipitates could be different from theta, as we shall see soon. It may not be the equilibrium theta precipitate, but we will get a fine distribution of precipitates. Now, to get this hardness, what we do is that we follow a 3-stage route. We first solutionize an as received material above the solvus line, say about 550 degrees Celsius. Then we quench the material to get a supersaturated solid solution along with an increased vacancy concentration. This increased vacancy concentration is important to note, because this gives us higher diffusivity of the substitutional alloying elements during the aging step, which is following next. And during the aging step, we heat the material to about 180 or 200 degrees Celsius to obtain a fine distribution of precipitates in the alpha matrix. So, my final goal is to produce a schematically, if I want to draw a fine distribution of precipitates inside the alpha matrix, which can effectively impede my dislocation motion and give an increased strength to the material. Now, there are some details to be considered when I try to plot my hardness versus the temperature of time of aging. So, this is the next plot we consider. So, log time implies that we are talking of the order of, say, for instance, a few hours right here in this regime to a few days of heat treatment. And originally in the experiment of which led to the discovery of this age hardening treatment, actually the aging was done at a room temperature, which is close to this kind of a curve, in which case you can see that the curve is always increasing. These curves we can think of as schematic curves, schematic master curves, and we will note later that more the actual curves are a little more complicated, but the important lessons from this aging treatment can be understood from these schematic diagrams. We note that in this case there are 3 kind of aging curves drawn, one at 20 degrees Celsius, one at 100 degrees Celsius, one at 180 degrees Celsius. With increasing temperature, you can see that the peak hardness is obtained at a less time. That means, now if I increase my temperature of aging, then I get, and of course higher means, of course I am still much less than 550 degrees Celsius or where I intersect the solvus line. I am much lower than the solvus line temperature. And in such a case, I get my peak aging. So, for instance, this is where the peak aging lies for the 100 degrees Celsius curve. This is where the peak age or the peak hardness curve lies in the 180 degrees, and with 20 degrees we have not yet reached the peak age even after quite a few days of heat treatment. So, this is of the order of days and more. So, this implies that if I want to obtain peak hardness in a short period of time, then I have to go for a higher temperature. So, this is my hardness plotted with respect to log of time as before, and this log of time implies that more the time I am spending in heat treatment, more is my capital investment. Therefore, I need to worry about my production rate. Therefore, I have to worry about the time and hardness and properties optimization. Now, second thing to be noted from this graph, apart from the fact that the more higher the temperature, the shorter the time for peak hardness to be obtained, as we noted from here to here, but also that the peak hardness itself is less. That means, if I age at a lower temperature, then I get a higher peak hardness. So, this 100 degrees Celsius the peak hardness is higher than at 180 degrees Celsius where my peak hardness is lower. Now, that means that I need to design a time temperature cycle such that I can get optimized hardness which I require for my application within a reasonable amount of time. So, this is something which is very important. That means, I have to design my heat treatment cycle so that I can get the requisite amount of hardness, but without having to wait too long for the heat treatment to be completed. So, this is of course, in this curve we are assuming that we are starting with a material which has been solutionized and quenched, and now we are just doing the aging treatment and we are plotting the hardness of the sample with various amounts of times of aging. That means that suppose I age for say this is now for instance a day for instance here, then I can note that after 1 day aging at 100 degrees Celsius I get a certain hardness. With longer time of aging say 2 days, 3 days etc., I can see that the hardness is increasing. But finally, the hardness after a certain peak starts to decrease, as you can see clearly from this curve. That means that it is futile for me to, suppose I am aging at 180 degrees Celsius, it is futile for me to age beyond the time where the peak hardness comes. So, I have to note this time T1 which is my optimum time, and I would not like to age my specimen beyond T1. So, why is this curve has this particular shape? Why is it that the curve is initially increasing and then decreasing the hardness? That is, initially of course, I have a specimen in which most of the strengthening is coming from solid solution strengthening. That means, all the copper is in the form of a solid solution in aluminum, and this is the regime of solid solution strengthening where there is no precipitation hardening. Finally, I can assume that very long times of aging, that now I have reached close to my equilibrium. That means, all the excess solute has now come in the form of precipitates, and that means that the amount of since the solubility of copper in aluminum is small at room temperature, that there is some solid solution strengthening, but most of the strengthening, most of the to be more precise, most of the solute has now come in has been precipitated out and is in the form of the theta precipitate, which we noted is the equilibrium precipitate. So, we are operating between two regimes where the regime start and the regime finish. In start, we have most of the solute copper in the form of solid solution, but in the end we have most of it in the form of the theta precipitate and very little is in the solid solution. Now, the regime below the peak hardness is called the underage state, and the regime above the peak hardness is called the overage states, and as I said, we would like to peak age a material, we would neither like to keep it in the underage regime or the overage regime. In this underage regime, there is a fine dispersion of precipitates which have been closely spaced, and with the increasing aging time, we would note that there is a coarsening of precipitates and therefore, the interprecipitate distance. So, this particle here has to be read as precipitate, we have an increasing precipitate distance. Therefore, initially we have a fine distribution of precipitates here in this regime, but here we have these precipitates starting to coarsen, and further if you wait long enough, these precipitates distance would increase, but they would get little coarser. So, this is what is happening, this is leading to a decrease in hardness after the peak hardness. So, what are the mechanisms involved and what are the kind of precipitates involved is something which we have to note. Now, three things we have to track while we are talking about the aging treatment. Now, one of course, number one, I have to worry about solution from the precipitate, the precipitation process. And in the precipitation process, first I have to worry about the precipitate crystal structure. Then I have to worry about the precipitate morphology, and especially I would worry about the precipitate interface characteristics. And the third thing I would worry about is the interprecipitate distance. Now, this aluminum copper system is a model system to study many complex processes occurring, and is a good learning curve to understand a lot of aspects of physical metallurgy. And this is because as you are doing the aging process, first of all, the kind of precipitate which comes out and its crystal structure could be different for different times of aging. So, three things are happening simultaneously. The crystal structures could be changing, each precipitate which forms, its interface characteristic could change. For instance, initially you could have precipitate which is coherent, later on you could have precipitate whose one of its phases could be semi coherent, and finally you could have incoherent precipitates. So, the precipitate interface characteristics also changing with aging time. So, what we are tracking is so with aging time, lot of complex series of sequences are happening, and this can broadly be brought into the category of crystal structure changes, changes to interface characteristics, and finally there is another thing we have to worry about is the interprecipitate distance variation, because that is what is finally going to determine that how much hardness I am going to get. Of course, what kind of precipitate, what is its crystal structure, all together, all have to be read together, because the mechanism operative leading to weakening of the crystal is dependent on all these three characteristics which we have written here. So, let us see what is happening. Initially, if my precipitate is coherent, that means dislocations can actually shear through the precipitate and by a mechanism known as particle or precipitate shearing. In other words, if I have a precipitate and I have a dislocation coming in, which we have seen before. So, I have my precipitate here and dislocation coming in which is normal to the plane of the board, and if this dislocation is moving in this direction, finally the precipitate would be sheared. We have seen this before, and therefore, such a precipitate, yes, will give you some impediment to the motion of dislocations, but will not completely impede the motion of dislocations. So, if you are plotting the precipitate radius or the particle radius, and the increase in strength, the CRS is increased, which is known as a critical resolved shear stress is increased. That means, how much stress do I need to apply on the slip plane to actually cause, or if you are doing a tensile experiment, it is on the slip planes, what is the critical resolved shear stress which is causing slip of dislocations, and this is being increased because now these precipitates are providing an impediment to the motion of dislocations, and if the particle is coherent, then it can be sheared, and the dependence of with particle radius of the CRSs looks like this. That means, with increasing particle radius, then you require a higher stress to shear the dislocations, because some of these precipitates themselves could be, for instance, these particles could be intermetallics. That means, the Pearl stress within the precipitate is higher. That means, the portion of the dislocation, for suppose I am talking about a dislocation line which is shearing through. So, this is my precipitate, and when the dislocation is passing through from here to here, and I am seeing that part of this dislocation line is within the precipitate, then this part faces a higher Pearl stress as compared to the part which is outside the dislocation line. That implies that now to drive the dislocation through the particle, I have to apply a higher stress or a higher resolved shear stress. Now, on the other hand, suppose these precipitates are large and incoherent, then these precipitates cannot be sheared. That means, the dislocations have to bypass them via Frank-Reed mechanism, and for this I would note that the stress actually decreases with increased particle size, and this is for the particle bypass mechanism. That means, I have one kind of a dependence for critical resolved shear stress for particles which are coherent, and another kind of dependence for particles which are incoherent, and we have noted that with increasing time, we have not yet noted, we will note that very soon, that with increasing time actually the precipitates tend to go from coherent to semi-coherent to incoherent. So, putting together these two pictures, the fact that in the low times regions typically you have coherent GP zones or precipitates. We have introduced a new term called GP zones, which we will see what it is very soon. And if you go to larger aging times, you actually have incoherent precipitates. Therefore, in the initial regimes you expect a bypass or the particle shearing mechanism to be operative, and for larger aging times the dislocation will have to bypass the precipitate. Therefore, if looking at the two dependence, that means one of the curves increases, the other curve decreases, a sum of these two curves should be one which looks like this, in which case it is going up and coming down. That means that now that because of the underlying mechanisms involved, because of the nature of the interface of the precipitates, you expect that there are going to be different mechanisms operative, which gives you a peak age at a certain optimum amount of time. It means I would not like to age beyond this time, so as to retain my maximum benefit in terms of the time of aging. Now, what is this GP zones? Is actually it is a disk of copper atoms which is now embedded in the aluminum matrix. The crude schematic is shown here. So, this is something between what we might call a local segregation into a disk and actually a true precipitate. So, this is the we call as a precursor for a precipitate. Okay. So, to once again summarize, the complex set of events that are happening parallelly or sequentially during aging process are increasing size of precipitates with increasing interprecipitate spacing. That means, when I am aging the material, the size of the precipitates is increasing, and this also implies that the interprecipitate spacing is also increasing. The interface progressively goes from coherent to semi-coherent to incoherent, and of course, when I am saying this, I am worried about a single kind of precipitate, and even as I told you, the kind of precipitate which also changes with increasing time. Initially, of course, we get the GP zone, which is like a segregation of copper atoms on the one-on-one planes of aluminum. Then later on you get a metastable phase, which is known as the theta double prime precipitate. Then you get another metastable phase, which is known as the theta prime precipitate, and if you wait longer enough or age long enough, then you will get the theta phase precipitate. In other words, here the process is very complex. The underlying sequence of events is also very complex, but I can broadly understand that I go from the supersaturated solid solution to a GP zone to theta double prime to theta prime and theta, and this implies all this sequence happens usually at when I age at low temperatures like 180 degrees Celsius. I also have to, as I pointed out, track the interface characteristic, which tend to go from coherent to semi-coherent to incoherent, and I also have to track the interprecipitate spacing. The overall two mechanisms which I said we have to worry about are the particle shearing mechanisms and particle bypass mechanisms. Therefore, if I have a coherent precipitate, you can have particle shearing, which gives you actually a low strength, but this strength increases with increasing precipitate size. And therefore, putting together all these data, we can see that actually the aging curve goes up and then comes down. Now, so let us start by understanding what is this GP zone and how this GP zone is different from some of the precipitates like the theta phase and for instance the theta phase, the theta double prime phase, and the phases which are coming later on in the aging sequence. So, this GP zones is a unique thing and which is not found if you age at high temperatures, but you only find it when you age at low temperatures, and we will say a few things about the GP zones next.